Hello everyone, Oleg is here. Welcome back to our calculus series. In our previous video we introduced the concept of boundedness and talked about infinitely large and small sequences. Today we'll talk about an extremely interesting property of sequences called convergence, and we'll define the concept of a limit, which is one of the most fundamental notions in mathematical analysis. Let us begin with an intuitive idea of what it means for a sequence to converge. Let's consider an example x sub n, which is n divided by n plus 1. On the x-axis we have the index of an element, and on the y-axis we have elements themselves. The first term would be 1 divided by 1 plus 1, it is 1/2. The second term would be 2 divided by 2 plus 1, 2/3. The third element will be 3 divided by 3 plus 1, 3/4, which is 0.75, and so on. So it will go further and further and further. For example, the 99 will be 99 divided by 100, so it will be very close to 1, but never reaching 1, of course. If you look at the terms of the sequence, you will see that they get closer and closer to 1 as the index n grows. We say the sequence converges to 1, and we call 1 the limit of the sequence. Informally, a sequence has a limit if its terms get arbitrarily close to some fixed value. And if a sequence converges to some real number, then it is convergent, while if no real number serves as the limit of the sequence, then the sequence is called divergent. So these are the terms which we're going to talk about today. We have an example of a sequence convergent to 1, this for example. Now let's look at a divergent one. Let's look at the sequence minus 1 to the power of n, so that the first element will be minus 1, the second element will be 1, the third element will be minus 1, the fourth will be 1, and so on. This sequence oscillates between minus 1 and plus 1, never settling on a single value. So no real number can be its limit, and this sequence diverges. So now my favorite part. We now give the formal definition of the limit of a numerical sequence. In our case, a sequence of real numbers. I emphasize that we're discussing sequences of real numbers and their limits when n tends to infinity. So the definition. A real number a is called the limit of a sequence x sub n if for every positive epsilon there exists a real number n such that for all indices after this n large, the absolute difference between the element and the limit is less than epsilon. If such a exists, we write limit for n going to infinity, x sub n is equal to a. And we call x sub n, the sequence x sub n, convergent. Lim is a special mathematical symbol called limit, from Latin limes, meaning boundary. Let's dive a bit into the notation. This notation is equivalent to the following. Element xnth tends to a when n tends to infinity. So in other words, when we increase index n, so we go to the next, to the next, to the next element, this element becomes closer and closer to the limit. In different locations, this is also written in a bit different way. For example, the n tends to infinity may be under the sign of a limit. This also means exactly the same. This may be the index, this may be right under the lim symbol, so this means exactly the same. Another note, in English language texts, sometimes the limit is denoted by the large capital letter L, so we will use them interchangeably. So sometimes you will see something like limit of something something is equal to L. You might also see alternative notations, such as when discussing limits of functions rather than sequences. I'll make a note on this later. There is also a great illustration of this on Wikipedia. So here we have some sequence. You can see that we have element 1, element 2, element 3, 4, 5, 6, and so on. So you can see on the x the index n, and on the y-axis we have the element itself. And this is an example of a sequence which converges to the limit a, which is this specific value. And regardless which positive epsilon, regardless how small it is we have, there is some index n 0, so that the sequence lies afterwards completely in the epsilon tube. So what it means that after some index, so this index is the border one, and afterwards the green one and all the following ones, they pass into this tube. The tube is just the a plus epsilon and a minus epsilon. For example, a may be 1 and epsilon may be 1/100th. And we can also find the smaller epsilon, for example 1,000th, and the new index, which will be later, so that the sequence is afterwards inside the tube epsilon. And under the last image you can see an alternative topological definition of a limit, that for each epsilon there is only finitely many sequence members outside of the epsilon tube. So you can count the number of elements around the tube, and all the other elements, all the next elements will be inside the tube, and their number will be infinite. So in other words, it describes a limit as a point such that infinitely many terms of the sequence lie arbitrarily close to it inside the tube, while only finitely many terms lie outside any given neighborhood of that point. This is a very elegant viewpoint, but matches the definition we gave above. There is an exercise to prove that the sequence x sub n actually has the limit of 1. And we have to do that using only the definition we gave above. So let's take some arbitrarily positive epsilon, which will be just epsilon more than 0. And we want to show and prove that the difference between an element and the limit is less than epsilon. So this is by the definition of a limit. Let's work with the left part of the inequality. We know that we want to prove that the limit is 1, so we can replace a with 1. And we know that each element of the sequence is n divided by n plus 1. And we can represent 1 as n plus 1 divided by n plus 1. So we have the same denominator. We can open this absolute value and we'll have 1 divided by n plus 1. And we want to solve this, so it's just a rephrase. So now let's apply some mathematical tricks. This is kind of a note on inverting inequalities. When dealing with inequalities, such like this one, we multiply both sides by the positive number n plus 1, and we will obtain 1 less than epsilon multiplied by n plus 1. Because both sides are positive and we multiply these by positive n plus 1, and n is always positive, n plus 1 is also, the sign remains the same. Then we divide both sides by epsilon. Because we never multiply or divide by a negative number, the direction of the inequality remains the same. And finally we can move 1 to the left side and we will get this inequality. And this is needed again to make sure that this inequality holds. Therefore, we can take the n large as the whole part of this right part of the inequality. So this is the right part, and therefore this inequality will hold for any n more than n large. Why? Because n is more than this fraction. N is the whole part of this fraction, so n is more than n. And as we discussed previously, this one is needed to make sure this holds. So therefore, by definition, the limit for n divided by n plus 1 is 1, when n tends to infinity. And we can prove this for some epsilon values. So let's take epsilon of 100th. So then the n large will be, as you may remember, this is 1 minus epsilon divided by epsilon, and the whole part of it. This will be 99. So starting from n more than n large, which is equal to 99. So this is n equal to 100, because n is a natural number which we use for counting. The terms of the sequence stay within the range of 0.01 of 1, of the value 1. Or in other words, the values of the sequence are different from 1 by less than this range. And we can calculate the same for epsilon 0.5. n large will be 1, so starting n equal to, x nth will stay within the distance of 0.5 of 1. And we can actually see this. Let's calculate the actual sequence values. So when n is equal to 1, we can calculate the distance of the first element of the sequence to its limit. The sequence is n divided by n plus 1, so it will be 1 divided by 1 plus 1 minus 1. So it is 1/2 minus 1, it is minus 1/2, and this is 1/2. And this is not less than epsilon of 1/2. So this is our epsilon, so this doesn't hold. Let's see what happens starting n equal 2. And it actually is equal to 1/3, which is actually less than 1/2. And the next, the n equal 3, n equal 4, for them the distance will be less and less than 1/2. So if we draw this once again, we can see that our limit is 1, our epsilon is 1/2. This is the tube, this is limit minus epsilon, this limit plus epsilon. So 1 plus half, 1 minus half. And we can see that starting from the second element, our values become laying within this tube. So this is the proof and the visual interpretation that the sequence has actually the limit of 1. Now let's look at some divergent sequences. If a sequence has a finite limit, it is convergent, as we said. A sequence that doesn't have a finite limit is called divergent. Divergence occurs in two ways. There may be no limit at all. For example, let's consider again this oscillating sequence, which starts from -1, then 1, and so on, and it doesn't settle to any single value. No real number can be its limit, so it doesn't converge. On the other hand, a limit may be infinite. So if the terms of the sequence grow in absolute value beyond any real bound, we say it diverges to infinity. Such a sequence is called infinitely large, and yes, it is exactly what we were talking about during the previous lecture. For example, the sequence n cube, which begins with 1, 8, 27, and so on, grows beyond any bound, and we can say that its limit is infinity when n tends to infinity. So with the increase of the index, the value of the sequence element increases to infinity. Hence, when a sequence fails to converge to a finite number, it is called divergent, either because no limit exists or because the limit is infinite. We have already touched on infinitely large sequences, but now that we have the limit notion, let us explore this more formally. For some sequences, the limit is infinity, as we have already mentioned. Namely, we say that the sequence x sub n tends to infinity if for any real number, e capital, positive of course, for some index onward, the terms of the sequence x sub n are greater in absolute value than e. Formally, this is an infinitely large sequence, and in other words, there is such an n from the set of natural numbers that for any index after it, the absolute value of sequence's value is larger than e. And as you may remember, this is exactly the definition of an infinitely large sequence. And now we just phrase it more elegantly with the limit. Interestingly, infinitely large sequences split into two subcategories. If all terms of the sequence are eventually positive and grow beyond any bound, we say that the limit of such a sequence is infinity or plus infinity. So we just add a sign prior to infinity to show that this goes to the positive side to infinity. Or in other words, for any positive e, there is an n from natural numbers such that for every index after that, the value of x nth is more than e. So the only difference with that is that we don't use the absolute value. So the absolute value was required to define the infinitely large sequence, while if we want to say that the sequence tends to infinity or its limit is infinity, we can define it from this. And vice versa. I will not repeat everything. We can say that if all terms of the sequence are eventually negative and their absolute value grows beyond any bound, we say that the limit of such a sequence is minus infinity. Everything will be exactly the same. We take the positive e and we say that x nth will be less than minus e for any positive number e large. Several important remarks which will be helpful for us in the future. So remark 1. Let x sub n converge and have a limit of a, then by definition the difference with the limit will be an infinitely small sequence. This is how we were denoting the infinitely small sequence during the previous lecture. And this is according to the definition. You can check this in the previous video. Therefore, every element x sub n of a convergent sequence limiting to a may be represented as the following. X nth is equal to the limit plus a nth, where a nth is an element of an infinitely small sequence a sub n, and vice versa. If we can represent x sub n as the following, where a sub n is an infinitely small sequence, then x nth tends to a, so its limit is a. This representation will be very useful for some theorem proofs. The limit of a numerical sequence has a natural geometric interpretation. Inequality, from the definition, is equal to minus epsilon less than x nth minus a, where a is the limit, is less than epsilon. So we have just opened the absolute value. And we can move a to the both sides, so a minus epsilon and a plus epsilon. This is the same what we have discussed talking about the tube, so a plus epsilon, a minus epsilon, and we can draw this a bit more simply. So x are actually the values of the sequence x sub n, and we have some a value. This is just some number 1, 2, 3, 10, and we have some area around it, a minus epsilon and a plus epsilon. So this is a segment. And if a is truly the limit of the sequence x sub n, then for any positive epsilon, starting from some index n capital onward, all the terms of the sequence lie within this segment. So we may have different values of x, but starting some index, all of them will be somewhere close to a within this segment from a minus epsilon to a plus epsilon. Before concluding, let us briefly recap the concepts introduced so far to avoid confusion. You may remember the concept of boundedness from the previous lecture. A sequence is said to be bounded if all its terms lie within a certain range, and we can define boundedness from below, from above, or both. We can draw our favorite sequence x sub n equal to minus 1 to the power of n, which oscillates. Or this may be, for example, sine of n. And you can see that this sequence is being bounded from above and from below, so it lies within some range, but at the same time it doesn't have any limit. So it may be bounded, but not convergent. We'll talk about this case more in the next video. Another concept to be compared is an infinitely small sequence, denoted as a sub n usually. It is called infinitely small or tends to 0 if its terms eventually become and stay arbitrarily close to 0. For example, 1 divided by n is infinitely small, and we can say that starting from some number, this will be closer and closer to 0. This is actually exactly the definition of a sequence that converges to 0. It's sometimes called a null sequence. And in standard real analysis, saying a sequence is infinitely small is another way of saying its limit is 0. So an infinitely small sequence is just a sequence with a limit of 0. And this is how they are connected. During the previous lecture, we talked about an interesting property of infinitely small sequences, that its multiplication to a bounded sequence is also an infinitely small sequence. So let's have some infinitely small sequence, for example 1 divided by n squared, and some bounded sequence, for example sine n, and we want to consider their multiplication, which will be sine of n divided by n squared. And during the previous lecture we proved that this should be an infinitely small sequence. So this one is bounded, it is between minus 1 and 1, and 1 divided by n squared is infinitely small. So according to the property from the previous lecture, their limit will be 0. And it's clear that we have a limit of 0, so it's also an infinitely small sequence, their multiplication. Now let's remember infinitely large sequences again. So a sequence x sub n is called infinitely large or tends to infinity if its terms eventually become and stay larger in magnitude than any arbitrarily large positive value. Usually we take e capital. So let's take as an example -1 to the power of n, but multiplied by n. This sequence is infinitely large, so you can see that its absolute value grows infinitely and becomes arbitrarily large, yet it does not have a limit equal to plus infinity or minus infinity because its sign oscillates. So a sequence may be unbounded and infinitely large, but this doesn't necessarily mean that the sequence has an infinite limit in the precise sense. So in summary, when we say a sequence has an infinite limit, this is not about this one, we mean its terms eventually stay above or below any fixed real number. Saying a sequence is infinitely large usually means its magnitude becomes arbitrarily large, which is true for this one. But if the signs doesn't settle, the precise infinite limit may not exist. So infinitely large sequences and infinite limits, they're related, but have to be used very carefully. To conclude, in this video we introduced the concept of sequence convergence and explored the definition of a limit, both informally and formally. We also discussed divergent sequences, including the idea of infinite limits, and we revisited important notions like boundedness and infinitely large and small sequences from our previous lecture. In the next video, we will dive deeper into the properties of convergent sequences, exploring various theorems that will help us work with them more effectively. I hope you found this helpful. Thank you for watching.